Here we have a problem where we have two tanks. The flow rate between these two tanks is 10 pounds per second. The source tank is 10 feet off of the ground. The discharge tank is 50 feet in elevation off the ground. For this example, both tanks are open to the atmosphere. The suction side pipe is 2-inch Schedule 40 commercial steel, and the discharge side pipe is 1.5-inch Schedule 40 commercial steel. The length of the suction line is 25 feet, and the length of the discharge line is 60 feet. We're told that the pump efficiency is 75%. Losses due to fittings, expansions, and contractions may be assumed to be negligible for this problem. So we don't have to worry about elbows, valves, again, entrances, or contractions. We want to determine the required horsepower of the pump and then determine the pressures before and after the pump, or the pressure increase that the pump imparts. So we've got a lot of information that's given here and properties that we need to incorporate. We need viscosity of water, and so I looked that up and put that in there. We are told the mass flow rate. We're told that both tanks are open to the atmosphere, and so we're going to use absolute pressure here. We're given the length of the pipes at the suction and outlet side, also the diameters. Note that the nominal diameters are different from the actual diameters, so you need to look these up and get those, make sure that those are correct. I'm using a nominal density, and then we are also going to need a roughness factor for our pipe. Now, this is similar to the problem that we worked a little bit earlier, but we have to include some frictional losses. Notice we're told that we don't have to include any frictional losses for fittings, expansions, and contractions. So elbows, contractions, expansions, we don't have to include those frictional losses, but we do have to include the frictional losses that are just due to flow through a pipe. So that is the difference between the previous problem that we worked. So the overall strategy is going to be to apply the Bernoulli equation between positions 1 and 2. It includes these head losses, and so one of the things we're going to have to do is to calculate linear velocities and Reynolds numbers and determine if flow is laminar or turbulent, so that we can then calculate these head losses. So the first thing we'll do as we look at this problem is bring up our Bernoulli equation, and we want to calculate the horsepower required by the pump. So that is going to be captured in the head added. There's going to be no head extracted, so we can neglect that term. What else can we do? Well, I've got some of these assumptions tabulated here. Both tanks are open to the atmosphere. So since both tanks are open to the atmosphere, P1 is going to equal to P2, and we're assuming that there's not the difference in atmospheric pressure at these different heights, 40 feet, is negligible. So these pressure terms are going to go away. Also, we can assume the water is incompressible, so the density is constant. What about our elevations? Well, we can set our elevation, set the datum at the pump. And so position 1 is going to be 10 feet, and position 2 is going to be, Z2 is going to be 50 feet. Again, there's no head extracted. We will need the velocity, as I mentioned, we will need the velocity of the water in the pipe so we can calculate the head losses. But the velocity of the water at positions 1 and 2 are essentially going to be 0. So that's one of the things that we've talked about before, that the velocity of the water in the tank at the surfaces is going to be essentially 0, even though there will be velocity, appreciable velocity, that we have to calculate inside the lines. So if we make all those assumptions in applying Bernoulli equation from 1 to 2, our Bernoulli equation simplifies quite a bit. And so what I've done is, instead of head added, I put head for the pump, and then head lost. So this is our Bernoulli equation. We want to solve for H pump, the head of the pump. And so what that means, we know what Z2 is, we know what Z1 is. We're going to have to calculate the head losses. And so the first thing that we need to do is we need to calculate the velocities of the water in the pipes, in the inlet suction pipe and in the discharge pipe. And so the first thing we need to do for that is to calculate the cross-sectional areas. So I've got the cross-sectional areas. We were given the mass flow rate, and because it's steady state flow, our mass flow rate at any point in these pipes is the same. And so we can solve for the linear velocity in the suction side of the pump. That's 6.874 feet per second. And then we can solve for the linear velocity in the discharge, which is 11.3 feet per second. And do a quick check. That makes sense because our inner diameter of the discharge is smaller than our suction. So once we know the linear velocity, we can then calculate the Reynolds numbers in both of these pipes. So the Reynolds number, remember, is rho VD over mu, or rho times the linear velocity times the inner diameter over the viscosity. And so we get a value of 1.236 times 10 to the fifth on the suction side and 1.587 times 10 to the fifth on the discharge side. Both of those are much greater than about 2300, and so our flow is turbulent. And so we can calculate our, since we know the velocity, we know the Reynolds numbers, we can calculate the friction factor. And so this is equation 19.16 in your Turton et al. 2018 textbook. And then we can calculate the head losses due to frictional flow. And so the equations are pretty involved here. But what we've done is we've taken those equations and solved for the friction factor on the suction side. So it's about 5.3 times 10 to the minus 3. And on the discharge side. And that is about 5.48 times 10 to the minus 3. And then what we can do is we can then directly calculate the head losses for both sides of the pipe. And so that is given here. So the head loss on the suction side is 2.28 feet. The head loss on the discharge side is 19.55 feet. Does that make sense? Well, we were told that the length of pipe on the suction side is 25 feet. The length of pipe on the discharge side is longer, so that makes sense. Also, the inner diameter of the discharge pipe is smaller, and so that is why the head loss on the discharge side is so much larger than the head loss on the suction side. On the suction side, we have shorter pipe with a larger inner diameter. So if we want to, we can calculate the power loss due to these frictional head losses. And so remember, we can do that by taking the head loss, multiplying by the weight of the fluid, and then multiplying by the volumetric flow rate. And so the problem didn't ask for this, but I went ahead and did this just so we could compare this to what we get when we eventually calculate the pump power that is required. And so we get 0.04 horsepower on the suction side pipe and 0.356 horsepower on the discharge side of the pipe. So almost about ninefold, almost tenfold difference in power losses. We can then, of course, in solving this problem, we need to calculate the total head losses, and so that's just summing up the head losses due to the friction, and so that's 21.836 feet. And then, of course, remember what we're trying to solve for is we're trying to solve for the pump head that's required. And so now we have all our terms. We've got the head losses, the total head loss. We've got our elevation changes, and so we can go ahead and calculate this. Solve for the head loss of the pump, or sorry, the head that's required for the pump, and that's 61.83 feet, 836 feet. And this can be converted to horsepower because remember, head added is energy. I should put added per weight of the fluid in joules per Newton. And then if we want to get the energy added, we take the head added, we multiply the weight, which is rho times g. It's not just mass, it's rho times g. And then to get the power, we take the energy added and we multiply by the volumetric flow rate. And so to do that, we can calculate first the volumetric flow rate. We are given, and we can use either the suction side or the discharge side, because remember the mass flow rate is constant, it's incompressible fluid, and so the volumetric flow rate is equal. And so we get a value of 71.896 gallons per minute for the volumetric flow rate. We can then calculate the power required in the pump to pump this fluid by multiplying the head times rho GQ. That's 1.124 horsepower. But what we have to remember is this is only the power that's required to move the water. This isn't the power that the pump is actually using to move the water. We are told that the pump is 75% efficient, and so it's not 100% efficient. So the pump is actually going to have to be sized larger to move this water, and so we take our power required to move the water and we divide by the pump efficiency, and you can see we get about 1.5 horsepower. The other thing that I wanted to point out, the reason why I did this intermediate calculation is you can see that about almost a third of the pump power is used to, almost 0.5 horsepower is used to overcome the frictional losses. So the rest of the power is simply being used to overcome the elevation change. Now we can calculate the pressure drop over the pump. And so we can do this. Let me bring all this over. Calculate the pressure at position 3 and position 4. And so what I have done, because we have the pipe is different diameters, what I've done is I've broken this up into two parts of the calculation. And so I'm applying the Bernoulli equation from position 1 to position 3 so we can calculate the pressure at 3. And then I will apply the Bernoulli equation from position 4 to position 2 so that we can calculate the pressure at position 4, and then we will calculate our overall pressure drop. So applying our Bernoulli equation from 1 to 3, the velocity at position 1 is equal to 0. The velocity at 3, we already calculated above, the U for the suction part of the pipe. We can set the datum at the pump, so our Z3 is equal to 0, and we can take our Bernoulli equation. We have our head loss. We don't have any head added, I should say, because our pump is not part of our system, right? Our system is just from the tank level, water level, to the inlet of the pump. We are not including the pump at all. So head added is nothing. Head loss. We calculated the head loss above for the suction side. And so that is what the suction side is. No head extracted. And then P2 here becomes P3. We do have a suction velocity. We do have a velocity here that we need to worry about. And then we have Z2. This is our datum level. And so Z2, or I should say Z3, is equal to 0. So this is what our Bernoulli equation reduces to. We know what P1 is. We know what Z1 is. We know what our head loss is. We know what the suction velocity is. We don't know what P3 is. And so to make this just a little easier, instead of doing algebra, I was lazy here and I used the root function, and we get a value of 17.724 psi. So notice this is atmospheric pressure, P1, and we have an increase of about 3 psi from position 1 to position 3. We then apply the Bernoulli equation between points 4 and position 2. All right, so between position 4 and position 2, the velocity at position 2 is going to be equal to 0. The velocity at the pump outlet, which is position 4, was calculated above. We're going to set the datum to the pump because we don't like to deal with negative values in our Bernoulli equation. So always set your datum at the lowest value. We have no head added because our pump is not included in this little subsystem that we have. Our head loss was calculated above. The head loss for the discharge line was calculated above. Of course, no head extracted. The velocity, as we mentioned, at position 2 is equal to 0, but we do have a velocity at position 4 at the inlet. And so our Bernoulli equation, again, it may be a little confusing because this is my general form, and then I am changing to the specific numbers of our system. But our Bernoulli equation simplifies to this equation, and what we are asked to calculate is what P4 is. And so here, P4, it was easy enough to not have to be lazy and just calculate what that is in MathCAD, and we get an answer of 43.99, or about 44 psi. So again, remember, this is absolute pressure. We're not dealing in gauge pressures here. So we now have P4. We have P3. We can calculate our pressure drop, or pressure increase, I should say, across the pump, and that is 22.26 psi. One of the other things that we could do, we could also calculate the pressure drop by applying the Bernoulli equation across the pump from position 3 to 4. So I did it by calculating P3 by applying it Bernoulli equation from 1 to 3, and then I applied it from 4 to 2, and then I took the P4 and P3 and subtracted those. We could also apply the Bernoulli equation across from 3 to 4. And so that's what this calculation does. And so when we do that, we have the P3 pressure head, velocity head on the suction side. Now we have to include H pump. All right, we have to include H pump, which we calculated above because our pump is now in our little system, our subsystem. P4 and discharge. Notice that the elevations go away because we are assuming that there's not much of an elevation change, a negligible elevation change across our pump. And so we do this calculation, and we apply our assumptions, we do some simplification, and we get a delta P of 26.26 psi, which is exactly what we got above. Notice that we do not need to know the absolute values of P4 and P3. We just combine those into one variable so that we end up with, if you look at this, you'd say, oh, I've got one equation, two unknowns, but really all we have is one unknown, the P4 minus P3. And so we can solve it that way. And finally, one of the last things I want to say about this problem is we did this a little bit differently than the simple problem that we did earlier, where number one, we did not calculate head losses due to friction. And number two, that earlier problem that we worked had the discharge line and the suction line with the same diameter. And if you look back at that video, when we calculated the head added for the pump, we added that, or sorry, I should say, when we calculated the delta P for that pump, we did the calculation from position 1 to position 2 across the whole system. And as I note here, the answer is the same as doing the Bernoulli balance from the whole system as it would be if we did it just across the pump. And so the reason we did that, of course, is because the suction lines and the discharge lines were the same diameter. But in this problem, they aren't. And so what we have to do is we had to do this stepwise application of the Bernoulli equation, either from, I go back up here, we had to do it from 1 to 3 and then 4 to 2, or just over from 3 to 4. So the reason is because if you look at these calculations below, the different velocity heads contribute to the difference in the head added by the pump versus the pressure difference over the pump. And so because the diameter of the discharge line is smaller, some of the pressure energy is converted to kinetic energy. And so if we look at the head added by the pump, that's equal to 26.8 psi. So if we were to calculate the head added by the pump and convert that to pressure, that'd be 26.8. Notice that our actual difference is 26.26. And so our difference is between the head added by the pump compared to the pressure difference is 0.547. If we look at the velocity head on the discharge side versus the suction side, notice that that is the same number that we get for the difference between the head added by the pump divided or compared to the pressure drop. So what this does is it shows that kinetic energy was generated at the expense of pressure because in this problem, since elevation was constant, there were no other head losses in the pump. So a little bit of a maybe an extra detail here, but what that shows is that when you have a system where you have different diameter lines in here, you need to be a little bit more careful and apply things stepwise versus assuming that you can go from the very beginning to the end. Again, in that earlier problem, we had no frictional losses and we had constant diameter lines throughout our system. This problem is a little more complicated.